Let's get a little crazy here. What about this example? Could we find the GCD? Could we simplify it elegantly? Why not? Let's try it. So, let me see. The top, I'm going to try to simplify it. The top I see is a 12. That's a 2 times a 2 times a 3. Then you have a y and a y. Then you have an x and an x and an x and an x. That's 4 x's. On the bottom I have a 3 and a 3. Then I have a y, 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 x, x, x. And all I do is I try to pick up the shortcuts to this, but believe me, you don't want to do the shortcuts until you own it. You want to understand it. This is the way to understand it. Write it all out and see what's common. I can see that 3 of the x's are common. What else is common? I can see 2 of the y's are common. What else is common? I can see a 3 is common. Let me see what else is common. There are 2's, and I have no more free 2's. There are x's, there's no more free x's. That's about it. And so I rewrite it like this. I put all the things that were left over, a 2 and a 2 and an x that was left over, and everything that was not left over. I had a 3, I had 2 y's, and I have 3 x's all over. On the bottom I had a 3 left, I had 3 y's, then I had a 3, I had y squares, and I had 3 x's. This is just rearranging. This of course was natural exponents and a little times table. And now I'm going to do this piece where we unglue the fractions. 2 times x over 3 times y to the third times 3 times y squared x to the third all over 3 times y squared x to the third. This is by Matt, and the rest of that is very familiar. You kill this by jot and kill the 1. So you get 2 times x all over 3 times y to the third times 1 by jot, and of course you can drop the 1 by MID. This becomes 2 times x or 3 times y to the third. Multiplicative identity. You're free to write 4 there if you wanted to use a times table. 2 times 2 is 4. Very nice, professional, and powerful stuff. And incidentally, let's take a moment here to review here the GCD concept. This tells you, as a side bonus, it tells us how to find the GCD between 12 y squared x to the fourth, 9 y to the fifth, x to the third. It tells me that the GCD between these two things, if these were fractions and this was on top or on the bottom, the greatest thing that I can cancel is a 3, check, a y square, check, and 3 x's, check. Yippee-ki-yay. That's the GCD. Okay, as a side bonus. Pretty nice, huh? That's the greatest common divisor concept. Elegantly derived by prime factorizing numbers into the prime pieces. All you do is expose the prime pieces, and then you can see exactly what's common by making a little circle, whatever's common. Okay, couple more examples for GCD. Suppose you wanted to find the GCD between these two things, 55 and 121. You would pretend, this is just for understanding purposes, you would pretend that it's a fraction with 55 over 121. And you prime factorize it. This is 5 times 11, 11 times 11. And then you would see what's common. What is the greatest thing that's common? Oh, the only thing I cancel there is 11, so therefore the GCD is 11. And you're done. Okay, it's a way of understanding the GCDs. Between 36 and 60, you would imagine that they were made up of, you had a fraction with 1 on top and 1 on the bottom. It doesn't matter which one. The common stuff will still be common even if one's on top or they're flipped. This would be 2 times 2 times 3 times 3, 4 times 9. On the bottom this would be 6 times 10. But wait, that's not really prime factorized. Let me do better. The 6 I can write as 2 times 3. The 10 I can write as 2 times a 5. Now it's prime factorized. Those are prime pieces. So what's common? I see a 2 common. I see another 2 that's common. And I don't see anything else. Oh wait, I see a 3 that's common. And that's about it. The things that are common is a 2, and a 3. Which is also known as 2 times 2 times 3, which is also known as 12. So 2 squared times 3 would be acceptable, or 12. That's the professional way to find the greatest common divisor between two numbers. Prime factorize them and look at the prime pieces and just pick up what's common, the greatest stuff that's common. Okay, again, you would pretend that they're as a fraction, y squared x to the fourth, 9y to the fifth, x to the third, and then you prime factorize it, 2, 2, 3, y, x, 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 3, 3, y, 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 x, 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 and then you start trying to pick up what's common here. 2 y's, a 3, that's all that's common. Okay, so the GCD would be 3y squared x to the third. Okay, this is just pretending that it's a fraction so that it'll help you understand what the GCD is and how to compute it. And we use the prime factorization thing to help us. Alright, some nice stuff. I could say one more thing that I should tell you. Oftentimes another famous use for prime factorization, here, let's try this. Let's try on a brand new. On a brand new one. So we use the prime factorization today for a few things. We used it to reduce fractions elegantly. We used it to compute the GCD elegantly, and another famous use for it is to factor by terms. So let me explain that a little bit. So if I had 5x plus 6x, you could say, whoa, it looks like someone distributed an x here. Maybe I could take out the x and that would leave 5 plus 6. This is called distributive law. Okay, so if this was a given term, so you could always factor out. Sometimes you could factor things out of each of the terms and undo the distributive law. This process is called factoring. The prime factorization is useful because sometimes it tells you what you can factor out. For example, suppose I had, here's another example. Suppose I had 12x squared plus 18 x to the third. Suppose that was given. I could look at each one of these and say, what are the prime pieces here? I have a 2, 2, and a 3 times an x times an x. And here I have a, this is 9 times 2, right? Or 6 times 3. The 6 is a 2 and a 3 and a 3. So that gives you this prime factorization. This is just by times table. And then you can see exactly what's common here. You could see that there's an x squared column, x common. There's also a 3 that's common, and there's also a 2 that's common, and I believe there's nothing else that you could factor out of both of them. So you could say, oh, this is 2, that's the thing that's left over, times 6x squared. That's all the common things put together. And over here you could say, oh, this is 3 times the rest of it, 6x squared. This is just by rearranging things. What I'm doing is I set up the GCD and I can see exactly what's common on both of them. I say, oh, looks like someone factored out a 6x squared, so it must be 6x squared 2 plus, there was an x there left, 3x. And this is by distributive law. So another famous use of the powerful idea of prime factorization is to factor terms, to see what's the greatest common thing that you can factor. It's exactly the same concept. If you had something like this, 12x squared over 18x to the third, what can you factor out of each piece? So you would say, oh, this is a 2, 2, 3, xx. This is a 2, 3, 2, 3, x, x, x. What's common? Oh, there's an x common, there's another x common, there's a 3 common, there's a 2 common. So the GCD is 6x squared. That's what you can factor out of both of them, 6x squared. Okay, it's a very professional way to see what you can factor. So I hope you've gained some appreciation of prime pieces that are useful for many things. This only scratches the surface, but at least in our class, in our algebra class, they're useful to reduce elegantly, to obtain the greatest common divisor, and to learn a little bit about factoring terms from binomials. And that's not the end of it. We'll do some more of these next time when we have to add fractions. Alright, we should stop here. We'll see you guys here next time. Peace.